In this video, I'll show you how to control the LLC converter. So we want to control the output voltage, and this can be controlled by changing the gain of the resonance tank. The gain of the half bridge and the transformer are constant, so we can neglect them when we're doing the calculations. So the gain of the resonance tank is given by this formula. And W, or omega, is the per unit value of the switching frequency with a base of omega r. And here is omega r, and this is M, and this is Q, the quality factor. So this is the plot that we get if we plot this function with Q equal to 0.3 and M equal to 6. You can find the script for this plot in the bio. By doing a first harmonic approximation, we get this circuit here for the resonance tank. And then we can derive that this is the voltage gain, which is shown in another video that I made. So M is constant and Q is varying with RE. So this voltage gain curve is dependent on Q, which is not constant. It depends on the output resistance. So if we have high load, the output resistance will be low, which results in a high Q. But we design the LLC converter such that we get a nice response even though we have maximum output load. So let's say that we have a quality factor of 0.3 at maximum output load, which means that this is the worst case voltage gain. Any Q lower than 0.3 would give a higher peak and also better response. So by looking at the voltage gain curve, we can see that by increasing the frequency, gain is decreased. And by decreasing the frequency, we get an increase in gain. So we can therefore say that a change in omega is equal to minus k times the change in gain. So if we have a wanted gain, we can just find the k to calculate the wanted change in frequency. So this k is estimated by a PI controller. So this is the control circuit that we're going to use. So we control the half bridge in order to control the output voltage. So the output voltage comes from the LLC, and then we compare it with the reference voltage, and then we get the error. So this error goes into the PI controller, and then we have a saturation. So we want to add a saturation because we want to operate to the right of the peak. Because to the left of the peak, the gain is decreasing with decreasing switching frequency. And we don't want to have a too high frequency because that increases losses. And we also want to have a anti-wind up because we have the saturation. So then we have a feed forward. It should ideally not be constant. It should actually be derived from this gain function, but it's quite hard and I think it will be complex, so you don't actually need the feed forward. It is optional. But what is important here is that we have a negative sign in front of the PI controller because the gain is inverse proportional with the switching frequency or the change of switching frequency. So then we have the wanted switching frequency. Then we just put that into the PWM, and then we get the gate signals for the MOSFETs. So now I will show you how to find the PWM because it's a bit different than for other converters because you're not controlling the duty cycle, you're controlling the switching frequency. So this is the PWM for the LLC. So we have a 50% for the duty cycle. This is without dead time, so you should ideally add that for whatever you're doing. And then we have the switching frequency here, which calculates the carrier. So for this example, I have a triangular carrier. So how you find the carrier is up to yourself, but this is just one pretty simple way. Not the best, but it's very simple. So first you integrate the switching frequency. So it's important that it is in radians. And then you use a sine block found in Plex or MATLAB. It just generates a sine wave with the given switching frequency and with an amplitude of 1. And then you do the inverse sine, which could also be found in Simulink or Plex. And then you just divide by pi and add 5. And then you have a triangular waveform, which goes from 0 to 1. So that was the controller. So we have the PWM here, So that was the PVM. So the input is the switching frequency in radians, and the output is the gate signal for the MOSFETs.